Welcome. Today, we're cracking open a really special part of the organic chemist's toolbox. We're talking about all the cool ways to prepare aldehydes. This is all about transforming different molecules into this incredibly useful functional group. So let's jump right in. So here's the game plan. Think of this as our master map for today's journey. Right in the center, that's our goal, the aldehyde functional group. And we're going to look at three major highways to get there. First, we'll start with acyl chlorides. Then we'll tackle nitriles and esters. And finally, we'll see how to do it starting with hydrocarbons. But hang on, before we start mixing things, we really need to understand what our goal is, and more importantly, what the big challenge is. You see, making an aldehyde isn't always straightforward. It's kind of like a chemical tightrope walk, and you're about to see why. Okay, so what exactly is an aldehyde? At its heart, you've got a carbonyl group. That's a carbon double bonded to an oxygen. Super common. But what makes it an aldehyde, its defining feature, is that the carbonyl carbon is also bonded to at least one hydrogen atom. Remember that CH bond? Because it is everything. It's the key to its reactivity, and as we're about to find out, it's also the source of our biggest problem. And this visual says it all. That little CH bond makes aldehydes super easy to oxidize. They just don't want to stop here. You hit them with most oxidizing agents, and they'll happily keep on reacting to become carboxylic acids. So the name of the game is control. Every single method we're going to look at is really just a clever way to hit the brakes and stop the reaction at exactly the right moment. So let's open the first drawer of our toolkit. We're jumping into pathway 1, making aldehydes from acyl chlorides. You'll probably hear these called acid chlorides too. Same thing. And the first tool we're pulling out for this job is a classic, a really famous named reaction you'll definitely see again. It's called the Rosenmund reduction. Let's break this down. We're starting with our acid chloride, and we're adding hydrogen. Now the real secret here, the magic ingredient, is the catalyst, palladium on barium sulfate. We call this a poisoned catalyst, which sounds bad, but it's actually genius. It means we've deliberately weakened it. It's just active enough to swap that chlorine for a hydrogen. Boom, we get our aldehyde. But, and this is the clever part, it's not strong enough to then reduce the aldehyde any further into an alcohol. It's a fantastic example of chemical finesse. All right, time to move on to our next set of tools. We're now heading down pathway 2, where we'll see how to whip up aldehydes from two different starting materials, nitriles and esters. First up for the nitriles, we have another famous named reaction. This one is called the Stevin reaction. Now, the key thing to get here is that this is a two-part process. You can't just do it in one go. First, we use stannous chloride and hydrochloric acid. This reduces the nitrile, but it stops at this intermediate stage called an imine. You can see it right there in the middle, the RCH double bonded to an NH. Once we've made that imine, all we have to do is add water, a step we call hydrolysis, and that cleanly snaps it into our final aldehyde product. But for more delicate work, for more precision, chemists often reach for a reagent called D-bol-H. That's a mouthful. It stands for diisobutyluminium hydride. Now just look at the molecule on this slide. It's got a nitrile group, yeah, but it also has a carbon-carbon double bond. A lot of reducing agents would just attack both, but not D-bol-H. It's selective. It goes straight for the nitrile group and leaves that double bond completely alone. It's like performing chemical surgery. And the versatility of Di-bol-H is really something else. It doesn't stop with nitriles. It's also an absolutely fantastic tool for reducing esters. As you can see right here, it cleaves the ester at a very specific spot and reduces it down to an aldehyde. This really makes Di-bol-H one of those powerful, multi-purpose tools you'd want in any synthesis kit. Okay, let's move on to our third and final pathway. This time, we've got a totally different challenge. We're starting with simple aromatic hydrocarbons. Think things like toluene or even benzene. And we're trying to figure out how to stick an aldehyde group right onto them. And our first method for this job, specifically for oxidizing that methyl group on a benzene ring, is called the Itard reaction. So, how does the Itard reaction solve that over-oxidation problem we talked about? Well, it's all about trapping the reaction halfway through. The reagent, the stuff called chromyl chloride, it reacts with toluene and forms that big, bulky chromium complex you see there in the middle. This complex is awesome because it acts like a protective shield. It's stable and it won't oxidize any further. So once we've formed it, we just add water, which breaks the complex apart and releases our beautiful product, benzaldehyde. Now there's another, very similar trick to get the same result. This one is known as the chromic oxide method.
This method takes a slightly different road to get to the same place. Here, we're using chromic oxide and acetic anhydride, and it's really important that we keep the temperature low. Instead of making a chromium complex, this reaction protects the intermediate by turning it into something called benzalidene diacetate. And just like before, this intermediate is tough. It resists being oxidized further. Then, a final hydrolysis step gives us our benzaldehyde. Simple as that. And this table just sums up those key differences really nicely. For the H-TARD reaction, you're using chromial chloride to make a chromium complex. For the chromic oxide method, you're using chromic oxide to make a diacetate intermediate. So you have two different reagents, two different protective groups, but it's the exact same underlying strategy. Trap the reaction before it has a chance to go too far.
Now, it's one thing to do this in a lab, but when you want to make tons of benzaldehyde on an industrial scale, chemists use a different, more direct approach. They do what's called a side chain chlorination of toluene. This makes something called benzol chloride. And from there, it's just a simple hydrolysis with hot water to get the final product. It's a really robust method that's just perfect for large-scale manufacturing. But what if you don't have toluene? What if your starting material is just plain old benzene? Well, for that, you need a completely different tool from the box, the Gattermann-Koch reaction. This reaction is just so cool because it actually builds the aldehyde group directly onto the benzene ring. You use carbon monoxide and hydrogen chloride gas with a catalyst, and it performs a process we call formylation, which literally just means adding a formyl group, which is our aldehyde group. It's an incredibly powerful way to go straight from benzene to benzaldehyde. Phew, okay, we've now gone through all three of the major pathways from our roadmap. So let's step back, put all of these tools on the table, and take a look at our master synthesis map. And this slide really brings it all home. You can see how all our starting points, acyl chlorides, nitriles, esters, toluene, and benzene all lead inwards. With amazing tools like the Rosenman reduction, D-Ball-H, the E-TARD reaction, and Gattermann-Koch, we have all these different routes leading to our central target, the aldehyde. This right here is your complete map for aldehyde synthesis. So we've seen a whole bunch of clever chemical tricks and a lot of famous named reactions, which brings us to one final question. Looking back at this whole toolkit, what's the one, single, most important idea that connects all these methods? What's the core strategy that lets chemists perfectly stop the reaction right at the aldehyde stage without going too far?